We've looked at what happens when waves move down the line and then come back, and even a little bit at what happens when waves meet up with each other. So we are talking about interference with that. This video is going to be about standing waves and resonance. We've been working with transverse waves, so that's the context of these for right now. We'll come back and do this again with longitudinal waves later. For right now, the idea is this. If I have a string, doesn't have to be a string, but that's what I'm going to use as an example. If I have a string and I send a pulse down the line, and it reflects and it comes back and we do all these things, then at some point, maybe I send a second pulse and a third pulse, I can start to build up patterns. Now I want to show you a quick simulation of what this can look like, or a quick animation of what this can look like. Here we have two red waves that are approaching each other. Once they do meet up, we see that they meet up in phase. And because of that, the blue wave shows kind of the buildup of the waves when they start to interfere with each other. So there are locations where we see that buildup lead to very high amplitudes. Like up here, these go all the way up to 2 because the individual waves that make it up go up to 1. And then if you look, there are locations like right here where the wave doesn't move at all. So we get this pattern of spots like at x equals 0, spots where we get our maximum and minimum amplitude, and then spots that stay put where we get nothing going on. Those spots where we get nothing are called nodes, and the spots where we've got a lot going on are called antinodes. I will pull this up again in just a moment. After this has been going on for a little while, the entire wave will kind of look like this, and we will have these locations. These red dots, again, are our nodes. We'll have these locations where the wave doesn't move at all, where the string doesn't move at all. And we've got these locations exactly halfway between the nodes. These are called antinodes, where the string moves the most. So we get this pattern, and because the nodes stay put, because the relative locations of these things stay in one spot, we call this thing a standing wave. It doesn't look like it's going anywhere. So let's see what we can get out of this pattern. When I did this, I was able to get some kind of a pattern like this, where I had a wave that did that. Now, over time, that wave kind of reflects, and we see the up and down motion. So this would be maybe the other major position of that wave. And what I like to do when I approach this is look at something like this right here and call this a loop. So when I have my string, and my string has a length of L, I can put some waves on this. So let me try this one. I'm going to go up and down, and then back up. What have I done? Well, one thing that I really want to point out, I said on the left side, I had to have my string be fixed. So on the left side, I'm going to have a node because the string is fixed. On the right side, my string is also fixed. So I have to have a node. And a node, again, is just where that string isn't moving. So when I do this, I have a node at each end. So I'm just going to go up and down and back up. I just have to start on a node and end on a node. Right now, I have one up wave, one down wave, and you know, over time this thing is going to vibrate kind of up and down. So it's going to look like that. If this is sped up, you're going to see it just kind of blinking real fast type of thing. And there is a certain frequency associated with that. Now what I have with this blue is I have two loops. I'm going to call this two loops. Here's one loop, Here is the other loop. So I've got those two loops, and those two loops take up a distance of L. My wavelength, if I trace out, I have right here, I've got an up and a down. That's one complete wave. My wavelength is always going to be exactly two loops. So my wavelength equals L. This is the frequency that gave me two loops, so I'm labeling it F2. Let's try something else. Maybe I increase my frequency a little bit. If I increase my frequency, remember I will decrease my wavelength, so I need smaller waves to fit on here. Right now, I can fit two loops on here, but maybe I can change the frequency so I can fit three loops on there. I can go up, down, up, and back. I'll draw out the other half of it. So now I have three loops. Call this thing F3. I'm saying three loops equals L, which means one loop equals L over 3. My wavelength, which is always going to be two loops, equals 2L over 3. And that's just fine. I met these things when I say that this is fixed and there's a node on the end. Is called a boundary condition. And in this case, because I have the same boundary condition on both sides, I'm going to call a symmetric boundary condition. We will talk about asymmetric boundary conditions a little bit later. I have right now these boundary conditions that say I need a node on each end. My blue met that condition. I've got a node on the left and node on the right. My red also met that condition. Node on the left, node on the right. I'm going to erase the blue and the red because these pictures get very overwhelming very fast. They get really busy. And I'm going to keep going with this. I could meet these same criteria if I went with 4 loops. Which would look like this. And I'm going to say there's a 4th frequency associated with that. When I do this, 4 loops take up my whole length L, which means one loop is going to be L over 4. My wavelength, which is always 2 loops, equals 2L over 4. And I'm sure that some of you will have written 2L over 4 as L over 2. Won't even have written the 2L over 4, just reduce the fraction right away, which your middle school math teacher would be very proud. But I wrote it as 2L over 4 for a reason. I have 2L over 4, 2L over 3, and then L. What if I write L as 2L over 2? I've got kind of a pattern going here. I'm going to erase this one and look at just one more. I started with 2 loops. That was my first one to draw. I could go from a node to a node in 1 loop. There's some frequency 1 that goes with that. Now 1 loop equals L. My wavelength, which is always 2 loops, equals 2L. And just to keep the pattern going, I'm going to call this 2L over 1. Now my pattern, I've got a 2L over 1, 2L over 2, 2L over 3, 2L over 4. You can see what this pattern is. So if I want to look at some later one, if I want to look at n loops, I would have 1 loop equals L divided by n. So maybe I'm looking at like 17. If I've got 17 loops equals L. 1 loop is 1/17 of L. My wavelength, which is 2 loops, would be 2L over n. And these are what my wavelengths are. This one I'm going to call wavelength 1. wavelength 2, wavelength 3, wavelength 4, and I'm just going to call this one wavelength of the nth. Now I would like to be able to give this a name because names are kind of nice, and these are called harmonics. N is called my harmonic index. So when I'm looking at n equals 4, I'm looking at my 4th harmonic. N equals 32 is my 32nd harmonic. That's all I'm looking at with that. These harmonics are a case of resonance, and resonance is just when we've got this particular kind of building up that's going to end up amplifying our system. And we saw that before with the simulation, right? When we had this wave coming in from the left and the wave coming in from the right, and they both had an amplitude of 1. When they met up in the middle, they suddenly had an amplitude of 2. Those waves add up. So what we see at resonance is this amplification of our signal. We achieve resonance when we have, in this case, a whole number of loops on our string. Those are stable patterns, and those will have set locations for the nodes. I'll do a little bit more with this. The speed of a wave on a string has its own equation, and that is the speed is the square root of the tension divided by the linear mass density of the string. What this means, if I've got a string that is 2 meters long, and it has a mass of maybe 50 grams, which is 0.05 kilograms, then I would have a linear mass density, which we unfortunately give the letter mu. Makes you think of friction, but it's not in this case. Mass over length is going to be 0.05 kilograms over 2 meters is 0.025 kilograms per meter. When I do this, most of the time I would have a string like this. It's going to be fixed over here, and maybe I hang this over a pulley and attach a mass. Because I attach a mass there, that holds this string under a tension, so I can get some kind of a tension force on top. But here's where I'm going with this. Whatever tension that is dependent on the mass that I hang there. On the mass that I hang there. Whatever the linear mass density of the string is, well, that depends on the string. Neither of those depend on the frequency or the number of loops. This equation isn't really one that you need to know necessarily. It's just good to see the equation to see that nothing's going to change. The point of this is to say, if tension is going to be constant and linear mass density is going to be constant, then my wave speed is constant. Now, I had this equation before that a wavelength times a frequency equals a wave speed. So I'm going to look at this and solve for frequency, and I'm going to say frequency is the wave speed divided by lambda. Now, I have already said that lambda is 2L over n, so I'm going to get this as a wave speed divided by 2L over n, and because nobody likes 3-story fractions, n times v over 2L. Still going, I promise. V over 2L, well, that's going to be the frequency of my first harmonic, right? If n equals 1. So this thing equals the frequency of my first harmonic, and because that's such an important thing, we call this a fundamental harmonic. With a fundamental frequency. it gets better. What I've said is that I solved for frequency, and that's the frequency of the nth harmonic. I have a formula now. The frequency of the nth harmonic is equal to n times the fundamental frequency, which I can put in purple. That's what I've been using. So if I find that I get a fundamental frequency, if I find that I can turn my frequency up to, I don't know, 20 hertz, and I get one loop in this string, well, my second frequency, I'm going to put in n equals 2. I'm going to go 2 times 20. That gives me 40. So my second frequency will occur at 40. My third one will occur at 60, which means the spacing between my frequencies is going to be equal to my fundamental frequency. And I can show you that too real quick. The frequency of, so let's say I have the frequency of the nth harmonic. And maybe I have a whole lot of loops on this string and I don't want to count them. But I can I can say that my frequency of whatever harmonic that happens to be is 175 hertz. Very slowly, very carefully, I turn my frequency up and I establish another resonance. And when I do that, I find that my next resonance occurs at 200 hertz. So my next resonance is at 200 hertz. Let's see what this means. If I take the difference between those, fn plus 1 minus f of n, I would get f of n plus 1 based on this equation is going to be n plus 1 times the frequency of my fundamental harmonic. F of n is going to be n times the frequency of my fundamental harmonic. And what I found was that this was 25 hertz. I needed a 25 hertz difference. I can distribute this n f1 plus 1 f1 minus n f1 equals 25 hertz. And I've got an nf1 minus nf1. So what I see here is that my fundamental frequency is 25 hertz. Whatever the spacing is between my frequencies, that's what my fundamental frequency is. So if I have one, if I find that I get, if I find these, then I can find the next frequency after that. I'm just going to add another 25. It's going to be at 225. I can also use this to then figure out which frequencies these are. So n times f1 equals 175 hertz. And I just found that f1 was 25 hertz. Which means n is 175 hertz over 25 hertz equals 7. I was looking at my 7th harmonic here. I drew a whole lot more than 7 loops, but it was to illustrate a point. I don't have to know what harmonic it is I'm looking at to be able to figure out the fundamental. Once I've got the fundamental, I can really figure out most anything. So this is Waves on a String. It's a long video, but a pretty complete one.